Hello, good people. How are you? Welcome to Physical Sciences Revision for your term 3. Today, I brought a question paper from the province of KwaZulu-Natal. It was for grade 11s. It was a question paper that came from the Department of Education, which was a common test for September 2024. And this question paper was supposed to be written in 2 hours, carrying 100 marks. Now you would see that here I also have got the instructions that were given to learners. Let's learn to read these instructions and follow. Like for example, they said you should start each question on a new page, and then they said you should leave one line between two subsections, for example, between question 2.1 and question 2.2. These instructions are guidelines of what they are expecting, so that when they are now marking, it becomes easier to follow through your answers. Also, here they said round off your final numerical answers to a minimum of 2 decimal places. Let's learn to read and follow these instructions, good people. So now we can actually get to see that this question paper had multiple choice questions, and then it was also having structured and open-ended questions. So for your multiple choice questions, we had question number 1.1 up to question number 1.5. And then for structured and open-ended questions, we're having 6 questions from question number 2 to question number 7. Let's get started. So for your multiple choice questions, they are saying that you have got 4 options, which is from A to D, and only one correct answer is for each of these options. So for the 4 options that you have, you are only going to get one answer, which will be correct. Now let's get to see what was the correct answer for 1.1. The question is saying the number of hydrogen atoms in 1 mole of ammonia is. You were supposed to actually get to calculate or determine the number of hydrogen atoms in 1 mole of ammonia. So the keyword to underline there, it's 1 mole. We know that in 1 mole, we have got 6.022 times 10 to the power 23 atoms. So we get to see that in terms of our mole ratio, how many moles are equivalent to hydrogen? There are 3. So to actually get to find the number of atoms of hydrogen in 1 mole of ammonia, you would come and say 3 times 6.022 times 10 to the power 23. So if you do that, your answer was supposed to be equal to 1.806 times 10 to the power 24. So the answer here was supposed to be C, 1.806 times 10 to the power 24. That was the answer that you were going to get. So if you punch in your calculators 3 times this, you are supposed to get. So your answer was supposed to be C. Now we are now saying which one of the following gases occupies the largest volume at standard temperature and pressure. So you would know that at standard temperature and pressure, the volume occupied by 1 mole would be given by 22.4 decimeter cubed. Mean to say that each and every mole of a gas will occupy the same amount of volume. So now we are now given the masses of each gas. So what we need to do here, we need to determine the number of moles of each gas so that we can determine which gas has got or else carries a larger number of moles. Then the largest number of moles correspond to the largest volume occupied by that gas. So let's get to say the number of moles of oxygen will be given by the mass of oxygen given by the molar mass of oxygen. So this one would be 32 grams divided by the molar mass of oxygen. We know that an oxygen atom carries a molar mass of an atomic mass of 16, which corresponds to your molar mass. Then you get to say 16 times 2. That becomes 32. So this one was actually carrying 1 mole of oxygen. And then what about for ammonia? You also calculate for ammonia. So for ammonia, you also get to come and do for what? For ammonia. So you would see that for ammonia here, it will be 34 divided by, it will be 14 plus 3 times 1, that will be 17. So it will be 34 divided by 17. This one was going to give you 2 moles. And then you get to say for nitrogen, that will be 7 divided by 14 times 2. So this one was actually going to be 7 divided by 28. So this one, 7 divided by 28, it was going to be less than 1. So 7 divided by 28, it was actually going to be 0.25. So here we're having 0.25. And then for helium, we also know that for helium, we would actually get to say that the number of moles for helium, it would be equal to 4 grams divided by the atomic mass of helium, it's 4. So this one was also going to give you 1 mole. So which one of these has got the largest number of moles? You would see that it was for what? It was for ammonia, which is B. So your answer, which actually answers the question which says, which one of the following gases occupies the largest volume at STP? It would be ammonia, because it is having, or else it is actually carrying the largest number of what? Of moles. So your answer there was going to be B. Now let's look at the following question. So your following question was 1.3 there, where you were actually supposed to deal with what? With the behavior of real and ideal gases. So now let's try to answer our question. So the question is saying real gas behavior deviates from ideal gas behavior at what? We know that a real gas will deviate from ideal gas when we have got what? Very high pressures, and then when we have got what? Low temperatures. So we are looking for an answer which has got high pressure and low temperatures. So for A, it was low temperatures and low pressures. This is out because we want low temperature and high pressure. Moderate temperature, this is out. And then moderate temperature as well, this is out. And then here it is saying low temperature and high pressure. So our answer was going to be D. Let's go to 1.4. In a chemical reaction, the difference between the potential energy of the products and the potential energy of the reactant is equal to what? So we get to say that the potential energy of the products minus the potential energy of the reactants. This one, it's more like you're just saying enthalpy of products minus enthalpy of reactants, and this one gives you the heat of reaction, which is the what? The enthalpy change of your what? Of your reaction. So the answer there was actually going to be what? We are looking for enthalpy change of reaction. So the answer was going to be C, because A says enthalpy of reaction, which is wrong. And then we get to go to say that rate of reaction, which is wrong. And then the answer would be enthalpy change of what? Of reaction. So the difference between the potential energy of your products and the potential energy of your reactants gives you the change in enthalpy of the reaction, because we are just saying enthalpy. So potential energy corresponds to the enthalpy of your products or your reactants. Let's go to question number 1.5. So question number 1.5 was saying that which one of the following is the correct description of a solution of hydrochloric acid of concentration 0.1 mole per decimeter cubed? Now, your options are saying dilute strong acid, dilute weak acid, concentrated. So here we have got our answers in terms of dilute and then our answers in terms of either strong or weak acid. So here we need to determine if hydrochloric acid is a strong or else a weak acid. So we know that hydrochloric acid is a strong acid. And the other examples of strong acids are sulfuric acid and your nitric acid. And then examples of weak acid are your acetic acid, which is vinegar, your benzoic acid, your citric acid. So those ones are your weak acids. Now, when it comes to dilute and concentrated solution, we know that if something is of a solution which is less than 1 mole per decimeter cubed. So why are we saying less than 1 mole per decimeter cubed? We are just looking for a range which will give us a minimum number of salt, a minimum number of the amount of your solute in the what? In the liquid. So at least less than 1 mole. So from something around 1.1 to somewhere around 1 mole per decimeter cubed would be dilute. Something that is greater than 1 mole will now be concentrated. So here they said 0.1 mole per decimeter cubed. So this is actually dilute. If this is dilute and we know that hydrochloric acid is a strong acid, our answer was going to be dilute strong acid. So our answer was going to be A. Now let's go to the following question. So our next question was question number 2. Now we are now on structured and open-ended questions. This is to say that you are not limited on the amount of words that you're going to use, or else on option A, B, C, or D. Now they said define the term molar mass. What is molar mass? What is molar mass? So you can see from molar. So we know that the number of moles is given by the mass of a substance divided by the molar mass. So what is this molar mass? So if I am to actually get to interchange these two, I would get that my molar mass would be equal to the mass of the substance per unit mole. So I'm just saying that the amount of substance that I have per each unit mole, or else per 1 mole. So molar mass can be defined as the mass of substance of a unit what? Of a unit mole. So you'd come and say that the mass of 1 mole of what? Of substance. So the mass of 1 mole of a substance is what we refer to as molar mass. This is mass per unit mole. Now calculate the percentage of carbon in cane sugar. So now they've given you the molecular mass, they've given you the molecular formula of cane sugar, and they want you to determine the percentage of this carbon in this compound. So how will we define our percentage in this compound? We need to determine the molar mass, the total molar mass of this compound. So the total molar mass of that compound was going to be equal to 12. We get to say that there are 12 in terms of mole ratio of carbon atoms. So you say 12 times the atomic mass of carbon, which is 12, plus 22 times the atomic mass of hydrogen, which is 1, plus 11 times 16, which is the atomic mass of what? Of oxygen. So the total number there was actually going to be equal to what? To 342 grams per each mole of that compound. Now, we now know the total molar mass of this compound. How much of carbon is in this compound? That is what they refer to as the percentage. So we actually get to say 12 times 12 divided by the total molar mass. So the answer there was now going to say, let me just get to scroll up so that we can find space to write our answer. So I would actually want to write my answer this side. So just allow me to rub there so that I can find space to actually get to write. So like I said, the first step is to calculate the total molar mass of the compound that we are given. So the total molar mass of the compound, we said that it's equal to 342 grams per mole. In that 342 grams per mole, we have got a total of what? Of carbon. So if we want to calculate the percentage of carbon, we would actually get to say 12 times 12 divided by the total, which is 342, times 100%. And this was actually going to give us 144 divided by 342 times 100%, giving us a percentage of what? Let's use our calculators. We are going to get a percentage of 42.11%. So the percentage of carbon in sugarcane was supposed to be 42.11%. Now, let's look at the next question. So the next question is now saying that uh, there is a compound which is CXH of Y is a compound made of carbon and hydrogen. So this compound, in terms of its mole ratio, it has got X moles of what? Of carbon, and then Y moles of hydrogen. And then now they are saying 1.97 gram of this compound reacts with excess oxygen to produce 6.8 grams of carbon dioxide. Now determine the empirical formula of this compound. So we can see that this one, it's a hydrocarbon. And when a hydrocarbon reacts with excess oxygen, that is what we refer to as combustion. So at some point in time, it's a reaction which might look something like this to form carbon dioxide plus your water, because this is the complete combustion of this compound. And we have been told that there is excess oxygen. So definitely this is going to react completely so that it can actually get to form this. Now the question is saying, determine the empirical formula of this compound. So we need to find these mole ratios. We need to find X and we need to find Y. To find X, we need to find the amount of carbon that is in this compound, which is carbon dioxide. So we can actually find the mass of carbon that is in here, and then we can actually get to subtract it from the total mass of carbon that you would find in this compound. So here we were going to actually get to determine the amount of carbon in terms of mass. So the mass composition of carbon here. And then after determining the mass composition of carbon, we then get to relate how this carbon is actually related to the carbon in here. So for us to balance an equation like this, we will need the total number of carbon atoms, or else the total number of carbon moles which are in our left hand to be equated to our right hand. So definitely here we're going to have X. So it simply means that the total amount of carbon that we have is the total amount of carbon that we are going to produce in carbon dioxide. So the mass composition of carbon in this carbon dioxide is the same as the mass that you are going to have in this compound. So let's calculate the mass in this, the mass of carbon in this compound. So we can say that in terms of mole ratio, I have got one atom of carbon reacting with two atoms of what? Of oxygen. So you would actually get to see that in terms of this, I would actually get to come here, and then I would say that my carbon has got a molar mass of 12, and then I would actually get to say that the total molar mass of this is actually going to be equal to what? The molar mass of carbon dioxide is equal to 42. So you will see that the mass composition of carbon, which is in this carbon dioxide, is going to be equal to, I'm just going to say carbon in carbon dioxide is equal to 12 divided by 44. So if I want to calculate the amount of carbon that is in 6.2 grams of carbon dioxide, I'll come and multiply by the mass of that carbon dioxide. So I can get the total mass that I have for carbon in carbon dioxide for this given mass. Then here I would actually get to find, let me punch my calculator. My answer was supposed to be equal to 1.69 grams. So we've got 1.69 grams of carbon in carbon dioxide. So we are forming 1.69 grams of carbon. Since we say that the mole ratio of carbon in this compound is equal to the carbon that is in that compound as well, we are going to simply say that the amount of carbon that I would be having here is the total amount of carbon that I'm going to form here. So if I'm forming 1.69 grams of carbon here, I'm also actually reacting 1.69 grams of carbon here. So the amount of carbon that I have in this compound is going to be the same with this. So what is the amount of hydrogen? So now we want to calculate the mass of hydrogen in that compound. So the amount of hydrogen in that compound is going to be equal to 1.97 minus 1.69. And this was going to give you a total of what? Let's actually get to use our calculators to actually find our what? Our total mass. So our total mass there was supposed to be equal to 0.28 grams. It was 0.28 grams. Now I have got the mass of hydrogen which is in this, and then I now have got the mass of carbon which is here. If that is the case, now I need to find the simplest mole ratio of these two. How do I do that? I usually get to advise that we use a table. So now we have the mass of hydrogen. So let me just get to draw a table that we're just going to use there. So at some point in time, I would be having my element which is in my compound, and then I would be having the mass of that element in that compound. And then I'll need to calculate the number of moles of that element in that compound so that I can actually now use the smallest number of moles to find the simplest ratio. So here, this will be a column for simplest ratio. So now the elements that I have, it's carbon, and then I would be having what? Oxygen. And then the mass, we have determined that the mass of carbon is 1.69 grams. And then the mass of oxygen, it's hydrogen, not oxygen. So here we have got hydrogen, and then it's 0.28 grams. Now to find the number of moles, we say this mass, which is going to be 1.69 divided by the molar mass of carbon, which is just 12, and then the number of moles that you are going to have there, you are going to have 0.14, 0.14. And then after having 0.14, you would come here also, you say 0.28 divided by the molar mass of hydrogen, that was going to be 1. So the number of moles was going to be 0.28. The smallest number of moles is 0.14 there. Let me just get to write that answer neatly. So the smallest, it's 0.14. If I say 0.14 divided by 0.14, I would get 1. 0.28 divided by 0.14, I would actually get what? If I say 0.28 divided by 0.14, it will be equal to 2. So my mole ratio, in my simplest mole ratio in terms of this, is actually 1 is to 2. So my empirical formula of that compound was going to be what? It was going to be CH2. That was the empirical formula that we were supposed to look for. So we can actually get to look back to the question and get to see what it actually highlighted for us. We were given this compound and the total mass of the compound, and then we're told that it is reacting with oxygen and later producing 6.2 grams of carbon dioxide, and then we're supposed to determine the empirical formula. So the first thing is to determine the mass of carbon in carbon dioxide by using the mass composition and then multiplying by the total mass of this compound. Thereafter, we compare the ratios, the mole ratios of the carbon, or else the number of atoms that I have, which is for carbon this side, and the number of atoms that I have for carbon this side. Then we get to see that the number of carbon atoms this side, they have to be equal to this side. So definitely the amount of carbon that I will produce this side would be equivalent to the amount that I would produce this side. So the mass of carbon that I would find here is the same that I would have here. So if I subtract, I would have the mass of carbon in this compound and then the mass of hydrogen in this compound. Then from that, I use my table to find what? The empirical formula. And I have actually shown you how my table would be looking like. So this would actually be my table where I list down the elements and then the masses that I have, the mass of this element in the total compound. And then I find the number of moles by saying the mass of this carbon divided by the molar mass. And then after finding the number of moles, I find the smallest. I divide throughout by the smallest to find the simplest ratio. And then the simplest ratio there was going to be 1 is to 2. So my empirical formula will be given by the what? By the simplest ratio between those. So let's go to the next question. So the next question there was question number 2.4. Now, 2.4 is saying a metal M forms two chlorides, which is MCl2 and MClX, that contains 55.9% and 65.5% chlorine by mass respectively. Now they are saying determine the relative atomic mass of M. So allow me to rub what we have done here so that I can actually get to use this space to determine the relative atomic mass for M. Now, to determine the relative atomic mass for M, what we are going to use is this percent composition. So we can see that we are saying that the percentage of these two chlorides is equals to 55.9% of this MCl2 and 65.5% of this. So what it simply means is we are simply saying that they said chlorine by mass. So you can see that these percentages are for chlorine by mass. So it simply says that the mass of chlorine, the total mass of chlorine that I have in my total compound, which is going to be the total mass of the whole compound, times 100 is supposed to be equal to 55.9%. So if I'm able to determine the what the mass of chlorine and then the total molar mass of this compound, I'll be able to find this. So what I'm given, or else what I can find, is the relative atomic mass of chlorine. So the relative atomic mass of chlorine is 35.5 from the periodic table. Let me just show you the periodic table here so that you can get to see where I'm getting that information. So from my periodic table, which is this one, I would go to chlorine. So chlorine is here, and then its relative atomic mass, it's 35.5. You can see from that periodic table. Now I have to come back to my question so that I can finish up. So my question is saying that I should find this, the total molar mass of chlorine molecule. So I would have 2 times this. So you would have came and said that 2 times 35.5 divided by the total molar mass of that compound times 100 equal to 55.9. And then if I divide by 100 throughout, I'll cancel out this, and then this side it will be divided by 100. And then if I get to interchange the molar mass of this total compound with this one, I would be left with 2 bracket 35.5 divided by, if I divide 55.9 by 100, I would get 0.559. So the total molar mass of this compound that I have here will be equal to 2 times 35.5 divided by 0.55. So to find that, I'll now get to use my calculator. Allow me to use my calculator there. So I would say that 71 divided by 0.559. And then my answer there was actually going to be 127. So here I was having a total molar mass of 127 grams per mole. So the 127 is including that for Cl2 as well as that for M. So for me to find M, I'll just get to say 127 minus the molar mass for Cl2. So I would just come here and say the molar mass for M would be equal to 127 minus the one for chlorine is just 2 times 35.5. So it would have been 71. And then if I subtract 71 from 127, I was going to get what? I was going to get 56 grams per mole. So that was the relative atomic mass for M. So the relative atomic mass was just going to be 56 grams. So this one was just going to be 56 grams. Because out of this molar mass, I'm going to remove that one for chlorine, and then I'll get for M. So for M, it was just going to be 56 grams. So allow me here to just get to say 56 grams. So given one more of this total compound, I was going to have what? 56 grams of what? Of M. So now calculate the value of X and then show all working. So now allow me to actually get to move this side. Now I would want to rub everything that I have this side so that I can be able to work. Now I just want to show you the part of the question. So we are doing 2.242. So I would actually get to say 2.42. Now you would actually get to see that for 2.42, they want the value of x. Now I'm saying that MClX, they said that the composition of chlorine in this compound by mass is equal to 65.5%. Now I now know the molar mass of M. So I can actually get to say that what it means is X times the molar mass, the atomic mass of chlorine, which is just 35.5, divided by the total molar mass of this, which would be the molar mass of M, which we actually found out to be 56. So we would come and say 56 here plus X times 35.5, because the atomic mass or else the molar mass of this would be this, and this is supposed to be equal to what? This is supposed to be equal to 65.5 divided by 100, because here would multiply by 100. So if we divide throughout by 100, it would be like this. So I'm looking for x. So all I need to do is to make x the subject here. So let's try to make x the subject. So in making x the subject there, I would actually take this one this side. So this one, if I divide it to be, so this one is more like 0.655. So if I take this one this side, it will be x times 35.5 being equal to 0.655 times all of this, which will be uh, so there, allow me to just get to create my space. It will be this is equals to 0.655 times 56 plus x bracket 35.5. And then thereafter, I just need to actually get to expand this bracket. So this one will be 0.655 times 56, and then thereafter plus x times 35.5 times 0.655. And then this side I still have this one. And then by doing that, I will now need to group like terms. I will take x times 35.5, and then I'll take this one that other side, and then it will be a negative x bracket 35.5 multiply by 0.655 being equal to this value, that would be 0.655 times 56. And then thereafter I'll factor out my x, and then I'll be left out with 35.5, subtracting this whole bracket here, 35.5 times 0.655, and then I would be left this side with the same value there, and then I would actually get to divide throughout by everything that I have this side, so that I can actually leave x alone. I will divide by that same factor this side as well. So these ones, they will cancel out. So the value for x that I'm going to find if I divide these, it was supposed to be equal to, if I punch in my calculator, the value that I found was equal to 3. So the value for x was supposed to be 3. And that is how we get to that 3. Now let's look onto the next question. So the next question is question number 3. So since this question is still on this page, allow me to rub everything here. Allow me to just get to erase. So now let's do question number 3. And question number 3 is saying that in an experiment, a 300 cubic centimeter solution of hydrochloric acid of concentration 0.5 moles per decimeter cubed reacts with calcium carbonate powder. The hydrochloric acid is in excess. So we have been told that using this equation, they're saying that the following balanced reaction takes place. So this equation is just describing what they've just said above, where in an experiment, a solution of hydrochloric acid was used in this concentration to react with what? Calcium carbonate. So this is calcium carbonate reacting with the hydrochloric acid solution to form these products. Now they are saying the volume of carbon dioxide gas produced is measured at regular time intervals, and the following graph is drawn. So this is the graph for the yield of carbon dioxide that we have in terms of its volume. So now we can see that there is volume of carbon dioxide as time is going on. Now they're saying define the term concentration. That is the first question. How do we define concentration? So the simplest notation of concentration is given by concentration as the number of moles per unit volume. So what is this? What does this mean? This is the amount of solute. This is the amount of solute which is dissolved in 1 decimeter cubed of what? Of liquid or else of solution. So if you are now defining concentration, you just come and say the total amount of solute in moles per unit volume of liquid. When you say unit, you mean 1 decimeter cubed. So you can actually get to say that your concentration is defined as the amount of solute. You'd say that the amount of solute in moles per decimeter cubed of liquid. So the amount of solute in moles that would be dissolved in 1 decimeter cubed of liquid. That is what? Or else of solution. That is what we refer to as concentration. So here we are given the concentration of what? We are given the concentration of hydrochloric acid. So this hydrochloric acid is actually having an amount of 0.5 moles in 1 decimeter cubed of what? In 1 decimeter cubed of water. So now let's hear what the questions are now saying. Give a reason why the graph is horizontal after 6 minutes. So the graph is horizontal here, where the volume produced is now 500 cubic centimeters. Why are we having this horizontal line? Or else, why our graph horizontal here? Why are we now having a constant what? A constant volume of what? Of our carbon dioxide. We now need to look into a reaction to get to see what's happening. So you can see that carbon dioxide is actually a product. So carbon dioxide is actually a product. So when we are now having a constant line, which is the horizontal graph of our product, it simply means that no carbon dioxide is being produced. So this horizontal graph tells you that no carbon dioxide is being produced. Why is it that there is no longer carbon dioxide being produced? We are told that HCl is in excess. We know that in a chemical reaction, we have got a limiting reagent and a excess reagent. So it's either we have got a limiting reactant, which might be this one, and this excess what? Reactant. So since they say this one is in excess, so it simply means that our calcium carbonate has been completely used up. Hence, therefore, there is no more carbon dioxide being what? Being produced. So you were going to write that answer in many ways. You would just get to choose. There is only one mark here. You can either choose to say no carbon dioxide is being produced, or you would come and say that calcium carbonate is a limiting reactant is now used up. It simply means that calcium carbonate is now finished. We no longer have calcium carbonate. So once our limiting reactant has been used up, then the reaction actually ceases. It stops. So once the reaction stops, it simply means that carbon dioxide is no longer being produced. Or else you would have just came and said the reactant, you would have just said the reaction has stopped. The reaction has stopped. So you would have chosen to write in either this way or that way or that way. So that is what it simply means for that constant line, or else for that horizontal graph. Now let's go to our next questions. So you see that the next questions are on this information, but they are now on another slide. So on my slide here, they are now saying determine the maximum number of moles of carbon dioxide gas produced. Take the molar gas volume at 25 degrees Celsius to be 24,000 cubic centimeters. So now, what is it that they want us to find? They want us to find the number of moles. How do you find the number of moles? At some point in time, let me just get to show you the formulation sheet. Our formulation sheet at some point in time helps us to just get to pick the relationship that has got the variables that you are given. So you can either find the number of moles in terms of this equation where you are given the mass of a substance and the molar mass of the total what compound, and then else you are given the number of entities of that substance and you know the Avogadro's constant, or else you are given the volume of that what of that substance where you know the volume at standard temperature and pressure. Now we have been given the volume at standard temperature and pressure, the molar volume, which is just equal to what they said, take it to be 24,000 cubic centimeters at what at 25 degrees Celsius, because that reaction is occurring at 25 degrees Celsius. So we have this and we are looking for this. So what we need to look to actually get to look into is, do we have the volume of what we want to look for? Now let's go back to the question and actually get to look at the information that we are given. So from this information, I want us to actually get to look into carbon. We are given this graph, and then the total yield, or else the total amount of carbon dioxide that was produced is equivalent to what? To 500 cubic centimeters. That is the total volume of carbon dioxide that has been produced. So we have this volume. All we need to do is to find the what? The number of moles. So we would actually get to come here and say that the number of moles was going to be equal to the volume of carbon dioxide which is being produced over the molar volume, which is at what? At 25 degrees Celsius. So we'll just come and say 500 cubic centimeters divided by 24,000 cubic centimeters. Mind you, here I'm using the same units. That's why I did not bother to either change this into decimeter cubed or change this into decimeter cubed. They have the same units. So the number of moles would just be simply this ratio. So 500 divided by 24,000 cubic centimeters per mole, you are going to get how many moles. So if you do that, you are actually going to get what? The number of moles that you're going to find was going to be 0.0208 moles. So that was the what? The total number of moles of carbon dioxide produced. since this is the volume that is being produced. And they are telling you that take the molar volume, the molar gas volume at 25 degrees Celsius to be this. So you know that if you are producing this volume and you know that this is your molar volume, it simply means that actually to actually get to find the number of moles, you divide this by the volume per unit mole. So this is the volume per mole of gas. So the total number of moles that you're going to find is what? 0.0208 moles. Now let's look at 3.4. Calculate the concentration of the HCl solution after 6 minutes. Assume that the volume of the solution remains at 300 cubic centimeters. Now they want you to find the concentration of HCl, given that the volume of HCl will remain to be that. But they are saying after 6 minutes. So you need to find the final concentration of the excess HCl. So you will see that at some point in time, our HCl is in excess. Since it is in excess, some of the HCl is going to react, and then some of them would be left behind. So the HCl that is going to remain is the one that is actually going to give us the concentration of the remaining. So how do we find this? We need to actually get to find the total of the excess, and then we remove the one that is reacting. So let's go back to our information. So the information here, just allow me to rub. Just allow me to rub there, so that you can actually get to see the information correctly, or else clearly. So here we are given the information that says that we have got a concentration of what? We have got a concentration of 0.5 moles of hydrochloric acid at a volume of what? Of 300 cubic centimeters. So we are simply saying that we have got 0.5 moles in a volume of 300 cubic centimeters. So what we need to do is to find the number of moles of this HCl, the number of moles of this HCl initially, the ones that we have initially. So this is going to be equal to 0.5 times this volume. This volume would be 300 divided by 1000, because we know that there are 1000 cubic centimeters in a decimeter cubed. So if we divide there and then we later multiply, the number of moles was supposed to be equal to 0.15 mole. So these are the initial number of moles of HCl. So this is the total HCl that we have in excess. And then now we want to see the number of moles of HCl that reacted. We know the number of moles of carbon dioxide that we produced. And then we can use the molar ratio of this reaction to find the number of moles of HCl that reacted. So the number of moles, the molar ratio there, it's 1 as to what? As to 2. So 2 moles of HCl are reacting to produce 1 mole of carbon dioxide. So the number of moles of carbon dioxide that we calculated were 0.0208. So it simply means that the number of moles of HCl that reacted are 2 times this. So the number of HCl that reacted would be 2 times that number of moles of carbon dioxide that is being produced. So you would see that here the number of moles of HCl were going to be 2 times this. So those are the ones that reacted. So for us to find the ones that were left, you now get to say that the number of moles of HCl final will be the number of moles of HCl that we were having initially minus the number of moles of HCl that we reacted. So this is going to be equal to these ones, it's 0.15 minus the value that we find by saying 2 times 0.0208 is actually equal to 0.04, it's supposed to be 416. So if I subtract these two, I'm going to find 0.1084 moles. So these are the number of moles of HCl that we will be having after 6 minutes. Finally, after our reaction is what? It's complete. So if this is the total number of HCl that we are going to be having at the end, now let's actually get to see what is it that they want us to find. So I'll take that answer that we found that other side to actually come to say that here we were having 0.15 number of moles of excess HCl, and then the one that reacted were 0.0416, and then the one that were remaining were now equal to, we said this minus this, and then it gives us 0.1084. If you add these, they should give you the total. Now, since we now know the number of HCl that is remaining, now calculate the concentration of the HCl after 6 minutes when the remaining volume is still 300 cubic centimeters. So we know that the number of moles are related to volume by saying we get to say that number of moles is equals to volume times concentration. From concentration is equals to what? Number of moles over volume. So if you want to find concentration, you would actually get to say number of moles divided by volume. So let me just get to find space to actually get to summarize everything that we have done there. So here we came for our, so this question was what? 3.4. So this one was 3.4. We said that the number of moles of HCl initially we calculated them by saying that the concentration times the volume that we're having, which is 0.3. You divide 300 by 1000, you get 0.3. And then this one gave us 0.14 moles. That was for the initial number of moles of HCl that we're having. And then in the reaction, we saw that HCl was having 2 moles reacting to form 1 mole of carbon dioxide. And then the total number of carbon dioxide that we found were 0.0208. So we would know that the number of moles of HCl that reacted will be equal to 2 times that of carbon dioxide, which will be 0.0208. And then this one gave us 0.04, it was 0.0416 moles. Since we now know the number of moles that were there initially and the one that reacted, the number of moles of HCl that was now remaining is equal to the difference of initial minus the one that reacted. So that was going to give us what? 0.15 minus 0.0416. The difference was going to give us 0.1084 moles. So this is the final number of moles that we have. Now to find concentration, would say the number of moles divided by the volume. So the remaining number of moles, it's 0.1084 divided by the volume that we have, which is also, let me just get to say 300 divided by 1000. Then the final concentration would be to say, if I divide these two, I was going to get a final concentration of what? I was going to get a final concentration of 0.361 moles per decimeter cubed. That was the concentration that I was going to get. That was the concentration that I was supposed to get for 3.4. And that was the final answer for 3.4. Now, having that is the final answer for 3.4, this was now question number 4. Now, I'll just get to give you at least 2 minutes to look into question number 4, where we just try to get to refresh. I actually want to connect my PC, it's on battery low. So I'll give you 2 minutes to just get to look into that question while we refresh. So I'm sure we've managed to actually get to look into that question. Now we are ready to just get to continue. So this is question number 4. And then after question number 4, we are going to go to question number 5, question number 6, and that will be the last question. So also allow me to just get to wrap what we've done here so that at least I can find space. So you would see that when it comes to grade 11, term 3, it's mostly chemistry. It's mostly chemistry. However, it depends with the school that you're attending. Your teacher might actually get to do the opposite, or else might actually get to choose to include or else not to include what we are doing here. But when it comes to the national matric syllabus for grade 11, using our ATP, these are the topics that you're supposed to be doing. Now let's do question number 4. A laboratory assistant prepares a solution of calcium nitrate of volume 250 cubic centimeters using calcium nitrate, using hydrated calcium nitrate, sorry. So this one is hydrated calcium nitrate. So they are saying that the laboratory assistant, he prepares a solution of calcium nitrate of this volume using hydrated calcium nitrate as the solute. Now they are saying that that calcium nitrate solution would be having calcium 2 plus ions as well as nitrate ions. Now they are saying if the concentration of nitrate ions, these nitrate ions in that solution is 0.15 moles per decimeter cubed, calculate the mass of solute that the laboratory assistant used. Good people, let's reread this question and let's actually get to follow exactly what they are saying. They want us to calculate the mass of the solute. And which one is our solute? This hydrated calcium nitrate. However, though, the information that we are given, it's for nitrate ions. So how do we end up here? We end up here by relating the amount of nitrate ions that you are going to actually get to produce out of this calcium nitrate. So this represents our solute in solution. So at some point in time, if I use the mole ratio of this as well as for that, I can be able to actually get to end up having the mole ratio of that, because this hydrated calcium nitrate is in a mole ratio of 1:1 as this calcium nitrate in solution. So if that is the case, now let's actually get started with answering the question. So here what I need to do is to find the number of moles. I need to find the number of moles of nitrate ions. I need to find the number of moles of nitrate ions. Allow me to rub here. So we know that uh, if you are having hydrated a hydrated solute, it simply means that that hydrated solute, it has got some water molecules that are trapped within it. So it simply means that if you dissolve that solute in solution, the solute is actually going to have the same number of moles as the actual calcium nitrate, because these ones definitely they don't dissolve. So what dissolves is this calcium nitrate. So that's the reason why I said once we are able to relate this calcium nitrate and the nitrate ions, we will be able to actually get to relate the number of moles of this with this, because the number of moles that are going to dissolve in solutions are the same, the ones that are here as well as the ones that are here. This is just the same thing. It's just that here it is having some water molecules trapped within it. We are having within the spaces of that crystal, there is some water droplets. So if you dissolve it in water, water becomes water. So this is the only thing that is going to dissolve to make the solution, which is this part. Now let's actually get to answer this question. So we are saying that let's first find the number of moles of these nitrate ions, since we are given the concentration of these nitrate ions, and then we are also given the total volume of the what? Of the solution. So let's get to use the information that we are given. So we are going to say that the number of moles of nitrate ions is going to be equal to the concentration of that nitrate ions times the total volume that we have of the solution. And that is going to be equal to what? That is going to be, here I've got 0.15 moles per decimeter cubed times the total volume would be 250 cubic centimeters divided by 1000 cubic centimeters in a decimeter cubed. So this will be simply 0.15 times 0.25. So this one was going to give you the number of moles were going to be equal to 0.0375. 0.0375 moles. Now we have got the number of moles of what? Of nitrate ions in that solution. Now we want to find the number of moles of this calcium nitrate that gave us this number of moles of these nitrate ions. So we get to say that if this calcium nitrate dissociates, it gives us 2 moles of nitrate ions from 1 mole of calcium nitrate. So you would see that the mole ratio there, it's 1:2. So if I know the number of moles of nitrate ions, I just need to divide by 2 so that I will know the number of moles of calcium nitrate. So I would come here and then I would say that the number of moles of calcium nitrate, the number of moles, I would say therefore, the number of moles of calcium nitrate are going to be equal to 1/2 times 0.0375 moles. And then the answer that I'm going to get there after dividing by 2, it will be 0.01, that's 0.01875. So with this, mind you, here I'm not rounding off because these are not my final answers. That's the reason why even before you would see me just carry a lot of brackets there. I don't just actually get to simplify, because these are not my final answers. I need to round off to 2 decimal places on my final answers. So now I have the number of moles of calcium nitrate. So like I said, if you dissolve hydrated calcium nitrate in solution, you are going to get the same number of moles of calcium nitrate as the number of moles that are in that hydrated calcium nitrate. So these number of moles here are the same with this. So since I now know the number of moles of calcium nitrate, I simply now know the number of what? Of the what? Of this solute. So now, since I now know this, I would actually get to say that the number of moles of my solute, so I will say the number of moles of my solute are simply equal to what? 0.01875. Now, how do I find mass? I know that number of moles is equals to mass divided by the molar mass of that same solute. So now my mass, I can actually get to make mass the subject. So my mass would be equal to the number of moles times the molar mass of the what? Of the total solute. So you would see that within my solute, I've got some hydrated, which is the water of crystallization, which is within that solute. So that is the molar mass that I need to calculate, the total molar mass. So you would see that if I show you this same compound again, you would see that I need to find the total molar mass of this whole compound so that I can be able to find the mass of this whole compound. That is my solute. So if I now come, I say for calcium, what is the atomic mass for calcium? What is the atomic mass for nitrogen, for oxygen? And then for hydrogen and for oxygen. We know that for hydrogen, for oxygen is 16, for hydrogen it's 1, for oxygen 16, for nitrogen is 14. And then for calcium, let's check for calcium, because calcium at some point in time, it's not most common. So that's when you would actually need to use your periodic table. Or for just assurance, you can use your periodic table for all of them to say for oxygen, I would come and take 16. For hydrogen, I would come and take 1. And then for nitrogen, I'll need to find nitrogen, I would come and take 14. Now I'm looking for calcium, I would come and take 40. So I now know the atomic masses for hydrogen, nitrogen, oxygen, and then this one was for the previous question that we did. Now I need for calcium. And then I then note them down. After noting them down, I then go back to where my question is, and then I get to fill in the information. So now I would actually get to say that for calcium, we said it's 40. And then for nitrogen, it's 14. For oxygen, it's 16. And then for hydrogen, it's 1. So now I now know for everything. So I now need to just get to fill in the information for this one. So allow me to go where we're doing so that we can continue. So for this solute, I would be having my number of moles, it's 0.01875. And then the molar mass there, it would be to say that it would be 40 plus for calcium nitrate, I would be having 2 times 14 plus 6 times 16. And then I would actually get to add for 2 times water, it would be 18. And then I'll get a total. And then thereafter, I'll need to find the final for those. So now the total final that I have for all of those, I will now get to say that the total that I have would be equal to 4.425 grams. That is the total mass that I've calculated. So that was going to be the mass of the solute. That was going to be the mass of the solute. Mind you, you are calculating for the total of the calcium nitrate, the hydrated calcium nitrate, not just calcium nitrate, but the hydrated calcium nitrate. So after that, we now need to look on our next question. So the mass there was just going to be 4.425. So you are looking for the total, which is 40 plus 2 times that, plus that, plus that, plus that. The total of this. So That total molar mass you multiply by the number of moles that you found here, and then you find your what? You find your mass of solid. Now let's go to the next question. 4.2 is saying that the chemical reaction for the production of aspirin from salicylic acid and acetoacid is represented by the balanced equation below. This is the balanced equation that is given. Now they are saying determine the limiting reagent. Just define the limiting reagent there. So for me to define the limiting reagent, let me just get to create space. I just need to define my limiting reagent. So allow me to define my limiting reagent there. Oops, I don't know what I've just done there. So sorry for that. I just uh, I just clicked somewhere where I was not supposed to be clicking. So now we are saying let's define the limiting reagent. So the limiting reagent here, uh, from our definition, we know that in a reaction, there is either an excess reagent or else a limiting reagent. A limiting reagent is the one that gets used up, is the one that determines when our reaction is going to stop. So the limiting reagent can be defined as the reactant that is used up in our what? In our reaction. Or else you can say that the reactant that is used up first in our chemical reaction. So once this reactant is completely used up, maybe you would have just added completely here. Once this reactant is completely used up, then the reaction stops. So that's the reason why I would say a limiting reagent would be the reactant that is completely used up first in our chemical reaction. And then the excess reactant just becomes that reactant that does not get used up in the reaction, or else that would be used up last. Now let's go to the following, which says by means of a suitable calculation, determine which of the reactant is the limiting reagent. So from this information here, we need to determine if salicylic acid or else acetic acid is the limiting reactant. So how do we do that? We need to first determine the number of moles of the product, or else the amount of product produced by each reactant. From the given information, we are given the mass of the salicylic acid that actually reacted and the mass of the acetic acid that reacted. That total amount of acetic acid that reacts, how much of our product is it giving us? When we find those quantities, we now get to compare which one gives us the smallest amount of product. That becomes our limiting reactant. So let me just get to create some space so that we can do that. So here, I need to determine, let's get to say the number of moles of what? Of salicylic acid first. So the number of moles of salicylic acid, GC7, H6O3, would be given by the mass over its molar mass. So the mass that was given there, I'm sure they'd say that the mass that was given for salicylic acid was just supposed to be equal to 14 grams, and the one for acetic acid, it's 10 grams. So those are the masses that we are using. So the mass for salicylic acid there, it's actually equal to 14 grams. So I have 14 grams of that. And then its total molecular mass, I will need to say 7 times 12, 7 times 12 for carbon, plus 6 times 1 for hydrogen, because carbon has got an atomic mass of 12, this one an atomic mass of 1, this one 16. And then I would come and say 16 times 3. And then the total number of moles that were going to be produced there were equal to 0.10 mole. So I was having the number of moles of salicylic acid that reacted were 0.1 mole. And then now let me calculate the number of moles, of acetic acid. I just want to create space this side so that I can have them side by side, and then we can be able to compare. So the number of moles of acetic aceto acid, let's get to say C4H6O3. So the mass over the molar mass would be, we are given 10 grams of it, and then the molar mass here will be 4 times 12. 4 times 12, that is just 48, plus 6 plus 16 times 3. If I do that, the molar mass that I'm going to get here also was going to be 0.1 moles as well. Now, we now need to compare the mole ratio of our reactants as well as the product. So you can see that the mole ratio of this one as to the product, they are 2 as to 2. So that's just 1 as to 1. So the number of moles that will be produced, so the number of moles of our product, which is, let's just get to say aspirin, that will be produced from the number of moles of salicylic acid that reacted will be equal to 0.10 moles, because they are in relation to 1:1. And then about this one and this one, we have got 1 mole reacting to produce 2 moles. So the number of moles that will be produced here, they are twice the number of moles that reacted for acetoacetic acid. So the number of moles of aspirin, let's get to say the number of moles of aspirin that were going to be produced from here, they were just going to be the number of moles of aspirin they were going to be 2 times 0.10 more. So you can see that this one produces, we are saying salicylic acid produces lesser number of moles of aspirin. Hence, therefore, it becomes our limiting reactant. So these are the these are the calculations that you are going to do. And then thereafter, you are just going to actually get to say that the number of moles. So you are going to say that the amount, you're going to say therefore amount of product produced from salicylic acid, which is C7H6O3, is less than the amount produced from acetic acid, which was just C4H6O3. Hence, this C7, that is C7. Hence, our salicylic acid, which is C7H6O3, which is salicylic acid, So let me just get to say that hence our salicylic acid salicylic let me the spelling there, let me just get to copy that spelling because at some point in time I'll end up writing the wrong things here. So that is salicylic acid. Yes. Salicylic acid is the limiting reactant or else limiting reagent. That becomes the limiting reagent. So we are saying that since the amount of product produced from salicylic acid is less than the amount of product that was produced from acetic acid, it therefore means that salicylic acid is the limiting reagent. Now let's do the following question. It says that the actual mass of aspirin obtained at the end of the reaction is 11.5 grams. Calculate the percentage yield of this reaction. So the percentage yield is just given by actual mass produced divided by the theoretical mass produced. So how do we find theoretical and how do we find actual? So let me just get to move this up. So we can actually get to say that our actual comes from the what? It comes from experience. So you would say that percent yield is equal to actual mass divided by theoretical mass times 100%. And then we know that theoretical comes from the reaction stoichiometry. It comes from the reaction stoichiometry. It comes from the reaction stoichiometry. So when we say reaction stoichiometry, we calculate this from the reaction. We calculate this from the reaction, while the actual mass is the one that is given where they said 11.5 grams. So what we now need to do is to calculate the theoretical mass that will be produced. Now, how do we calculate the theoretical mass with the given information? How do we calculate the theoretical mass with the given information? We can see that they gave us the given information, which is this equation. Now we can actually get to choose to relate with our limiting reactant. So we say this is our limiting reagent. So that is the one that we are going to use to actually get to find the simplest ratio in between this, the simplest reaction ratio. So you see that this one is reacting 1 mole of it to produce 1 mole of this, or else you can say 2 moles of salicylic acid react to form what? 2 moles of aspirin. So the amount of moles of salicylic acid that reacted are the same amount of moles that are going to be produced. And we calculated this and we found that they were 0.10 moles. So if we have got 0.10 moles being produced, what is the mass that is being produced? We now get to say that number of moles are equal to mass over molar mass. So to find the mass that is being produced theoretically, we now get to say the number of moles times the molar mass of this. And what would be the molar mass of this? We get to calculate the molar mass by multiplying 9 times 12 plus 8 times 1 plus 4 times 16. And then we get the theoretical mass. So let's go and calculate the theoretical mass. So our theoretical mass, since we now already know the amount that is produced, so we get to say the number of moles of the aspirin that is being produced. So we are looking at the number of moles of aspirin. That one has got 8. And then that one has got what? That one on top, it was having 4. And then the number of moles, it's 0.10. So we need to calculate the molar mass of this. So the molar mass there would be given by 9 times 12 plus 8 times 1 plus 0.4, 4 times 16. And then we will find our molar mass there is going to be equal to 108. And then thereafter, we need to actually get to find our mass. So the mass, which is the theoretical mass is going to be equal to 0.1 mole, because this is mole, times 180 grams per mole. And then this one was going to give you, so if you use units there, it becomes easy to know. So this one is grams per mole. For each mole, you've got this mass. So you are saying 0.10 mole times 180 grams per mole. These ones will cancel out, and then you'll be left with your units in grams. So the total mass that you were supposed to find there was supposed to be equal to 18.26 grams. After that, we now get to say 11.5 divided by 18 times 100. That is the theoretical yield. So to find the theoretical yield, to find the percent yield, we now have got our theoretical mass and our actual mass. We get to say that the percent yield is now equal to actual 11.5 grams divided by the theoretical, which is 18.26 grams, times 100. And then this was going to give us 63.90%. So that was the end of question number 4. That was the end of question number 4. Let's go to the next question. So question number 5 now, we are now saying that a group of learners perform an experiment to verify a gas law. The results of the experiment are shown in the graph of pressure versus the inverse of what? Of volume. So at some point in time, they're saying pressure versus the inverse of volume. And then they're saying, name the law being verified. So we know that the law that is being verified, that has got this relationship, is known as Bose law. That is the law that is being verified, where we are saying that pressure varies inversely proportional to the what? To the gas volume. So the name of that is just Boyle's law. That is the name of the law that is being verified. Now let's go to 5.2. 5.2 is now saying that write down an investigative question for this experiment. So an investigative question would be to say, what are we investigating with the Boyle's law? So the Boyle's law says that pressure varies inversely proportional to the what? To the volume. Meaning to say that as my pressure is increasing, my volume is what? My volume is actually decreasing. So if I'm actually saying that, it means that at some point in time, for me to know that, I would have asked myself, what is the relationship between pressure and volume when we have something constant? So we would come and say, the question would be to say, maybe let me just get to write it below here, to say the investigative question would have been to say 5.2. What is the relationship? What is the relationship between pressure of a, let's say, confined, I want to say confined or enclosed gas of an enclosed gas and its volume of a confined or enclosed gas and its volume, given that the temperature remains constant. Given that the temperature given that the temperature remains constant. That would be an investigative question that we would have came about with, to say that what is the relationship between the pressure of an enclosed gas. To say enclosed, it just means fixed mass, so that we don't get to have interaction with the what? We don't get to have interaction with the outside system, so that we get to say that our system is just closed. So we are using a fixed mass. So what would be the relationship between pressure and volume, given that the temperature remains constant? That would have been the investigative what? Question. Now they are saying name two variables that must be kept constant during this experiment. We have just mentioned that you have to have a fixed mass. So you are saying that you should have a what? Fixed mass. And then the temperature as well has to be constant. So the variables would be mass and temperature, your fixed mass and your temperature. Now calculate the volume occupied by the gas when the pressure exerted by the gas is 200 kilopascals. Now here we are using the what? We are using the graph to just get to determine that volume. So you can see that here, let me just get to say that the relationship is pressure is varying inversely proportional to that. So this can actually come to say pressure is equal to what? 1 over V. So I have got a pressure of 200 kilopascals, which is 200,000, equal to 1 over my volume. So I need to find this value of my volume at some point in time when I've got 200 kilopascals of pressure. So at 200, it's here, and then the value would be along here. It would be this one. So if this is the value, I can see that these are 10 boxes. So if 10 boxes are representing 1 unit, I would have to count how many boxes I have here. 1, 2, 3, 4, 5, 6, 7. So at some point in time, I'm at 6.7 times 10 to the power of what? Minus 2 cubic centimeter per cubic centimeter. So I know that 1 over V is equals to that. So what becomes my volume? My volume will just become 1 over this value, 6.7 times 10 to the power minus 2 per cubic centimeters. So whatsoever volume that I will find, it will be in cubic centimeters. So let's go down and write it neatly. So I found my value there for my inverse of volume. So I would come here and then I would get to say that 5.4 1 over V is equals to 6.7 times 10 to the power minus 2 per cubic centimeter. So if I want to find this volume, I will make this volume the subject. So I will interchange these two. So my volume would be equal to 1 over 6.7 times 10 to the power minus 2 per cubic centimeter. So that my volume would be in what? In cubic centimeters. So my volume here was just going to be equal to 14.93 cubic centimeters. That was my volume. Now they are saying determine the pressure exerted by the gas when its volume is 11.11 cubic centimeters. So if I have got 11.11 cubic centimeters, it will be easier if I use that law that we have just investigated now. So let me use the law because I now know the volume 1. So I'm saying that 5.5, since I can say P1V1 is equals to P2V2. I've got my volume 1 and my pressure 1, which was 200,000 kilopascals, the one that I used there. And then I found the volume of 14.93 cubic centimeters. I now want to find the pressure. So the pressure here, since this one is in pascals and this one would be in cubic centimeters, I would find the pressure in what? In pascals. And then the volume here is 11.11 cubic centimeters. I will just have to divide throughout by that 11 cubic centimeters. I divide by 11.11 cubic centimeters. This one they cancel out. So my answer here my pressure to was going to be equal to, uh, I was going to have something like 268. I was going to have something like 268.88 or something. So let me say 268.89 kilopascals. I've divided by 1000 already. So this was going to be 268,890 pascals, or else 268,89 kilopascals. That was going to be my volume there. As my pressure, so the pressure that I was supposed to find when I've got this volume was going to be 268 kilopascals. Now state two properties of an ideal gas. State two properties of an ideal gas. So we know that an ideal gas has no volume, and then it has no intermolecular forces, or else also you can say that the speed of the particles there, that speed is just the same. But for a real gas, we say that the speed is different. So for ideal gas, we get to say that it has no volume, or else you can say that the particles have the same speed. Since we know that from Brownian motion, gas particles are always in motion, so that motion would be of the same what? Of the same speed. Or else you would have just came and said they have no intermolecular forces. No intermolecular forces. They have no intermolecular forces. Ideal gases have no intermolecular forces. Now let's go to the question number 6. We are almost done, guys. This is the second from last question. The question is now saying, so this is energy and change. Once you start seeing these diagrams, it's energy and change. The graph below shows the energy changes for a certain reaction. Study the graph and answer the questions that follow. Is the reaction exothermic or endothermic? So we need to determine, or else to define, what an endothermic and exothermic reaction are in terms of this. So we know that an exo releases energy. So an exothermic reaction releases energy. And then an endo absorbs energy. So if that is the case, we know that for an exo, we know that our delta H, since it releases energy, it simply means that at some point in time, here we are also going to have energy. So since our reactions, they occur in a closed system, this is where our reaction is occurring in a closed system. The total energy there is conserved. We know the law of conservation of energy. Energy is neither created nor destroyed. So it means that what you entered, what you actually fed your system with is what you are going to get at the end. So the energy of the reactant has to be equal to the energy of the what? Of the products. So we get to see that if now the products are going to have energy aside, it simply means that the energy of these products are less than the energy of the reactants. So we get to see that this becomes less than 0, where we get to say H of what? Of products minus H of reactants is less than 0. So it simply means that H of products is less than what? H of reactants. So this H of products, when it's less than H of reactants like this, it simply means that here our delta H is going to be less than 0, and this is going to be an exothermic reaction. So this one was an exothermic reaction. The answer here was just supposed to say exothermic reaction. And the opposite becomes true, to say that once the enthalpy of products becomes greater than the enthalpy of reactants, it becomes an endothermic reaction. So this one was an exothermic reaction. Let's move to the next. Define the term of define the term activation energy. So activation energy, this is just the minimum amount of energy that you need for a reaction to occur. So you come and say minimum amount, minimum amount of energy required for a reaction to occur. And then now let's go to the next. The next question is now saying write down the values of the following. Now we now need to use that graph to determine the values of this. So allow me to actually get to try. So maybe I'll try to actually get to what? Yes, to position it in this way, right? And then I would get to rub some of the things there on top on this graph so that we can be able to see what's happening. So now let's look. So we have already defined this. Let's look onto energy of the reactants. The energy of reactants is this one. So here you're just supposed to have what? 208.2. They said it's in what? In kilojoules. Kilojoules. That was the answer there. Energy for products is this one. It was going to be 86.5 kilojoules. And then activation energy for the reverse reaction. So you can see that this reaction, you can see that this is the same reaction, but the other one is not catalyzed and the other one is catalyzed. The one with the minimum activation energy, it's what? Is the one that is catalyzed, because a catalyst actually lowers the activation energy of the what? Of the reaction. So you can see that this one, it's uncatalyzed. That's why it is having a higher peak, whilst this one is having a lower peak, so it's catalyzed. So when you are now going reverse from products to reactants, you will actually get to go through the uncatalyzed one, because catalyst, they are specific, so they will be specific to the forward reaction. The backward reaction will not be catalyzed. So now to find the activation energy of the backward reaction, you would need the amount of energy of your reactants, and then you get to subtract it from the amount of your energy at the peak there. So it was going to say that activation energy for the reverse, it was going to be 240.8 minus this value 86.5, and then these ones will be in what? In kilojoules. That is the activation energy of the reverse reaction. So you were just supposed to find the difference there. So the difference there was supposed to give you what? If you punch in your calculators, you were supposed to get 154.3 kilojoules. So these ones now becomes the reactants of the reverse reaction. And then you say the amount of energy at peak minus that of reactants. That's when you get your what? Your activation energy. So now here you are just going to say the answer there was just 154, the one that you have just found there. 154.3 kilojoules. And then now they're saying activation energy for the catalyzed forward reaction. Catalyzed forward reaction is this, and then the peak is there, the reactants are there. The difference in between these two, it's actually what? 217.3 minus 208.2. And what becomes that value? That value has to be equal to 9.1 kilojoules. That is the activation energy for the catalyzed reaction. What about the energy of the activated complex in the absence of a catalyst? So the activation energy of the activated complex in the absence of a what? Of a catalyst. So in the absence of a catalyst, the activated complex would be where? The activated complex, you would find it here. That is where you would find it. In the absence of a what? Of a catalyst. So the activated complex would be here. So its energy would be equal to that, which is equal to what? 240.8 kilojoules. That is how we were going to answer these questions. Now let's look at the following questions. Calculate the heat of reaction of the reverse reaction. Now the heat of reaction now of the reverse reaction, you were just going to say that the heat of reaction, which is delta H, it was going to be H of products minus H of reactants. That is how we calculate our delta H. So H of products is just 86.5 minus H of reactants 208.2. This is in kilojoules. And then your answer there was just going to be equal to what? Because for the reverse reaction now, it does not matter either it is going to be catalyzed or uncatalyzed. The change in enthalpy there is the same. So the change in enthalpy here was just going to be 127.7 kilojoules. Oh, sorry. They said for the reverse reaction. So for the reverse reaction, now this one was for the what? This is for the forward reaction. So the reverse reaction, you just do the opposite of what we have just done here. Your reactants are now these ones, and your products are now these ones, because you are reversing. So these ones becomes your reactants, these ones becomes your products. So it was just going to be 208.2 minus 86.5, and that one being in kilojoules. So the answer there was just going to be 121.7 kilojoules. That is the answer for that. Now let's do the last question on this question. What effect, now they're asking, what effect will the addition of a catalyst have on the energy of the products? It does not affect the products. So here we are supposed to choose increase, decrease, or remain the same. The catalyst does not affect anything to do with the products. So the energy of the products remains the same. The energy of the products remains the same. So we are saying that the energy of the products remains the same. And then the heat of reaction. Now, when it comes to the heat of reaction, they say that what effect will the addition of the catalyst have on the heat of reaction? Heat of reaction, which is delta H, remains the same, because we are just simply saying H products minus H reactants, for which the catalyst does not affect this enthalpy, it does not affect that enthalpy. So this one will remain the same. What is only affected by a catalyst is the activation energy. Now here they're saying the activation energy for the reverse reaction. Yes, if the catalyst is for the reverse reaction, this will actually get to decrease. So the only thing that is affected by a catalyst is the activation energy. So these were the answers for question number 6. Now let's go to question number 7, which is the final question of our question paper. Wow. Let's do this, guys. Let's just get to finish up. Given the following acid-base reaction, which is your ammonia reacting with your phosphoric acid to form ammonium and hydrogen, this is hydrogen phosphorus. Now we get to say, define a base according to the Lowry-Bromstead theory. So there are two people who defined acids and bases. The first one was Arrhenius. He said that water dissociates to form H3O plus OH minus, or else H plus ions. And then he said that if you are now to dissolve a substance and that substance increases these H plus or H3O plus ions, then it means that it's an acid. But if it increases the ions of OH minus, then it becomes a base. And then now, in addition to Arrhenius' theory, because they saw that now for you to start defining acids and bases according to Arrhenius, you needed to be in solution, meaning to say that you needed to dissolve those in what? In water. And then there are some acids that don't dissolve in water. How do we get to classify them? That's when these guys came to say that an acid can be defined as a proton donor, whilst a base can be defined as a what? A proton what? A proton acceptor. So a Lorry Bronsted base will be defined as a what? As a proton acceptor. Proton acceptor. So you define a base according to the Lorry-Bronsted theory by just saying that it is a what? A proton acceptor. You would say that a Bronsted base, or else a base according to the Lorry-Bronsted theory, it's a proton acceptor. Now they say identify the two bases in the above reaction. So according to Lorry-Bronsted theory, the ones that donates H plus. So you can see that H3 now comes H2. So it is donated in H plus. So this one is a what? It's an acid. And then this one becomes a base because it received. And then this one, now you would see that you would come here and then you get to see that now when you come this side, now you would be having what? You would be having this as a what? As an acid, because already it has got NH4 plus. It is increasing the what? The H plus ions. So this one becomes an acid this side, this one becomes a base this side. So two bases would be ammonia and H2PO4 minus. And then now they're saying define the ampholyte. This is a substance that can either be an acid or a base. It acts as both. A substance that acts as both an acid and a base. It can be an acid in a certain reaction, it can be a base in another reaction. For example, you have water. Water can be a base when it's reacting with hydrochloric acid. It can actually be a what? An acid when it's reacting with ammonia. Now they are now saying that write down the formula of an ampholyte in the above reaction. So in the above reaction, the ampholyte here would be this one. Why? Because this H2PO4 minus can either donate an H plus and then it will remain as what? HPO4 minus. Or else at some point in time it can receive an H plus, and then when it receives an H plus, it will now go back to become what? Phosphoric acid. So here it was a base, and then here it was an what? An acid. So you were just supposed to mention this one. This is the formula of a what? Of an ampholyte above here. Now, a learner reacts 20 cubic centimeters of 0.2 moles per decimeter cubed solution of sodium carbonate completely with 12 cubic centimeters of hydrochloric acid solution. The balanced equation of this reaction is given below. Now let's hear what they want us to do there. Now they are saying calculate the number of moles of sodium carbonate. How do we find the number of moles? We know that concentration is equals to number of moles divided by volume. So if I want to find the number of moles, I will just get to say the number of moles of sodium carbonate is equal to the concentration of that sodium carbonate times its volume. So here we are given 20 cubic centimeters of sodium carbonate and a concentration of 0.2 moles per decimeter cubed. So I need to convert these into decimeter cubed. I would divide by 1,000. So I would come here and then this one, I would come here and then I would say that the number of moles would be simply equal to 0.5, 0.2, that is 0.2 moles per decimeter cubed times 20 cubic centimeters divided by 1,000 cubic centimeters. These will form a decimeter cubed by cancelling out. And then the number of moles that I'm going to form there was going to be equal to 0.004 moles. That is the number of moles of what? Sodium carbonate. Now, concentration of the hydrochloric acid solution. We now need to find the concentration of the hydrochloric acid solution. This one was the number of moles, mind you. So 7.22 would be to say the concentration of what? Concentration of HCl. How do I find concentration of HCl? Let me read again. They say that this actually reacts completely with 12 cubic centimeters of hydrochloric solution. So if it reacting completely, now I need to find the reaction ratio mole. So you would see that 1 mole of sodium carbonate is reacting with 2 moles of hydrochloric acid. So if I know the number of moles of sodium carbonate, I will just get to multiply by 2. I would know the number of moles of HCl. So by knowing the number of moles of HCl as well as its volume, I would actually get to find the concentration by just saying that the concentration is equal to the what? To the number of moles divided by volume. At some point in time, you would also have used this Ca over Va divided by the coefficient, stoichiometric coefficient in this reaction of what? Of A. Let's get to say this one is A, this one is B. Will be equal to CbVb divided by the stoichiometric coefficient of B. And then those two formulations, they will give you the same answers. They will give you the same answers because it's the same thing. So if that is the case, now I would just come and say that what is the concentration of A? The concentration of A there, we said it's equal to 0.2 times the volume of A. We said the volume of A is 20 divided by 1,000. And then the coefficient of A here, it's 1. And then we say equal to the concentration of B. We are told the concentration of B there, the concentration of B that has been given, they said it's equal to what? Let's get to check there. The concentration of B there, we are not given the concentration of B. That is what we are looking for. We are not given the concentration of B. That is what we are looking for. So the concentration of B, we leave it like that. The volume of B, it's 12 cubic centimeters. So we divide by 1,000. And then we actually get to come to say what is the stoichiometric ratio there. It's 2. The stoichiometric coefficient is 2. So for me to find CB, I would actually get to make it the what? The subject there. So I would cross multiply by 2 and then divide by 0.012. So you would see that the answer there was going to say CB was equal to 0.2 times 0.02 divided by 0.012, and then I multiply by 2. And then the concentration of B, which is the concentration of HCl, that's the one that you are looking for, was now going to give you, the concentration was going to give you 0.67 moles. if you come here, you say the number of moles that you found there, you said you were going to say 2 times 0 point, the number of moles that you had found was 0.04 divided by the volume, which was 0.012. This was also going to give you 0.67 mole per decimeter cubed there. So you can see that the two answers are the same. So you can either use this where you say the concentration of reactant A times the volume of reactant A over the stoichiometric ratio of A equal to concentration of B times volume of B over the stoichiometric ratio of B. Or else you calculate the number of moles of the substance that you are looking for, and then you then get divided by the volume of that, and then you get that. Now they are saying calculate the pH of the hydrochloric acid solution before it reacted. Now, how do we find pH? How do we get to find pH? How do we calculate pH? We know that pH is the logarithm of H plus ions, or else H3O plus ions. So pH of a substance is equal to the logarithm of what? H plus ions, or else logarithm of what? H3O plus ions. That that substance, or else that compound, would actually get to make in solutions the amount of the H3O plus ions that are made by what? By that acid. Now let's go and try to find the concentration of the what? Of the H plus ions. So the concentration of the H plus ions are just going to be equal to the what? Because they say that before it reacted. So before it reacted, let me just get to show you something here. So before HCl reacted, it was having how much of the H plus ions? It was having the H plus ions that are equivalent to the number of moles that are within here. So those moles are the same, that are going to give you the same concentration as the concentration of HCl. So you would see that if HCl dissociates, it will have H plus and Cl minus. So the concentration that you are going to have of the H plus are equivalent to the concentration of what? Of HCl minus. Of HCl, sorry. So we are going to take the concentration of HCl initially, that would be equivalent to the concentration of H plus ions that are going to be what? To be formed. Why am I saying that? Let me just get to move this, and then I will show you the dissociation of HCl. So the dissociation of HCl is just given as HCl dissociates to form H plus aqueous plus Cl minus aqueous. So you would see that the molar ratio between this and that, it's 1:1. So the concentration of HCl will be equivalent to the concentration of what? Of the H plus ions that are formed there. So if that is the case, I'm allowed to use the concentration of the what? The concentration of the HCl that I found before. So here I was just going to say natural log of 0.67 moles per decimeter cubed. So this one was going to give me in the pH of what? 0.17. So we know that a pH is a number from what? A pH is a number on the scale of either Z, which is what? A negative up until 14. So here we have got, sorry, from 0 up until 14. And then 7 is the neutral. So here we have something that is on what? 0.17, just before 1. So you can see that this HCl is actually a what? A very, very strong acid. Because we know that this side I have got acid, this side I have got base. So that was our question paper, guys. Thank you for being together. Let's meet again next time.